Physics uses energy everywhere. Every equation, every interaction, every transformation. From the motion of planets to the decay of particles, from chemical reactions to black hole dynamics, energy appears in every calculation physics makes. It is conserved. It is transferred. It is converted. It determines how systems evolve and how processes unfold. And yet physics has never explained what energy physically is. Not how it transforms. Not how it is conserved. Not how it is measured. Only that it is there. In physics, energy appears as a quantity assigned to a system. A number that remains constant under certain conditions. A scalar value that can be calculated from motion, position, fields, temperature, or mass. It is written into equations as kinetic energy, potential energy, thermal energy, field energy, rest energy. The equations work with extraordinary precision. They allow spacecraft to escape planetary gravity. They allow engineers to design nuclear reactors. They allow chemists to calculate reaction rates, and physicists to predict particle collisions to many decimal places. But nowhere in those equations is energy itself defined as a physical substance or entity. Energy is calculated. Energy is conserved. Energy is transferred. But energy is never described as something that exists in the same way matter exists. In classical mechanics, energy appears in two principal forms, kinetic and potential. Kinetic energy is associated with motion. Potential energy is associated with configuration. A raised mass has gravitational potential energy. A compressed spring has elastic potential energy. A moving object has kinetic energy. The total energy of a system is the sum of these contributions. If no external forces act, that total remains constant. But what is this conserved quantity? When a ball falls, gravitational potential energy decreases, while kinetic energy increases. The numbers change, but the total remains fixed. The calculation is clear. The conservation law holds. Yet the question remains, what is it that is being conserved? The equations do not say. They describe relationships between measurable quantities. They specify how velocity contributes to kinetic energy. They specify how height contributes to potential energy. But they do not identify a physical medium or structure that energy corresponds to. Energy functions as an accounting rule, not as a defined constituent of reality. In thermodynamics, energy appears again, now in the form of internal energy. Heat flows from hot to cold. Work is done by expanding gases. The first law of thermodynamics states that energy cannot be created or destroyed, only transformed. The principle is universal. Every closed system obeys it. But the first law does not explain what energy is. It states only that a certain numerical quantity remains constant under transformation. Heat is transferred. Work is performed. Temperatures change. Pressures adjust. The bookkeeping remains balanced. The ontology remains unspecified. In electromagnetism, energy resides in fields. An electric field stores energy. A magnetic field stores energy. The Poynting vector describes how electromagnetic energy flows through space. These calculations allow engineers to design antennas, lasers, and communication systems. They allow physicists to calculate radiation emitted by accelerating charges. The energy density of the field can be written down explicitly. But what is that energy? Is it a substance, a property, a measure of capacity, a mathematical construct? The equations describe how field values determine energy density. They do not describe what physically constitutes that energy. In relativity, the role of energy deepens. Mass and energy become equivalent. A stationary particle possesses rest energy proportional to its mass. Energy contributes to gravity. The stress-energy tensor determines how space-time curves. The geometry of the universe depends directly on energy. Stars bend space-time because of their energy content. Radiation gravitates. Pressure contributes to curvature. Energy is no longer just a bookkeeping tool. It becomes the source of gravitational influence. Yet even here, energy is represented mathematically. It is a component of a tensor. It is inserted into field equations. It determines curvature through precise relationships. But the equations do not say what energy physically is. They describe how spacetime responds to it. They do not describe what it consists of. In quantum mechanics, energy appears as an operator. The Hamiltonian governs time evolution, and the energy eigenvalues determine the allowed states. Systems occupy discrete energy levels. Electrons and atoms transition between these levels. Photons are emitted with energies equal to the difference between the states. The predictions are exact. Spectral lines match calculations to extraordinary precision. But energy in quantum theory remains a numerical quantity associated with states. It is the generator of change. It determines how wave functions evolve. It is not introduced as a physical substance. It is a parameter in an equation. Even the uncertainty principle relating energy and time does not define what energy is. It constrains the precision with which energy can be specified over short durations, and it governs measurement limits. It does not describe what energy is. Across all these frameworks, energy is indispensable. Remove energy from physics, and the equations collapse. Conservation laws vanish. Dynamics disappear. Predictions lose coherence. Energy is fundamental to every theory. Yet no theory includes a physical description of what energy itself is. Energy is always defined relationally. It is defined through motion, through configuration, through fields, through temperature, through mass, through frequency. Energy is not defined independently of these. It has no standalone ontology. Consider potential energy. A mass raised above the ground has gravitational potential energy. Lower it, and that energy converts into kinetic energy. But where was the potential energy stored? In the mass? In the gravitational field? In the configuration of the system? Different formulations assign it differently. Some treat potential energy as residing in the field. Others treat it as a property of the system configuration. The calculations agree. The ontology varies. Energy shifts between mathematical descriptions without a clear physical carrier. Or consider chemical energy. A fuel molecule contains chemical energy. When it is burned, energy is released as heat and light. But the energy was not hidden inside the molecule as a substance. It was encoded in the arrangement of atoms and in the electromagnetic interactions between them. Energy is inferred from differences in configuration. It is not extracted as a material component. In particle physics, collisions convert kinetic energy into mass. New particles emerge when sufficient energy is available. The equations of quantum field theory allow this conversion precisely. Energy determines what particles can be produced. Thresholds are calculated, and outcomes are predicted. But the conversion does not reveal what energy is. It reveals that certain numerical values permit certain outcomes. Energy functions as a constraint, not as a defined entity. The conservation of energy is often traced to symmetry. If the laws of physics do not change over time, then energy is conserved. This connection is formalized in Noether's theorem. The mathematics is elegant. Time translation, symmetry, implies energy conservation. But this theorem relates properties of equations to conserved quantities. It does not define the physical nature of what is conserved. It explains why energy remains constant under certain symmetries. It does not explain what energy physically is. Even zero-point energy. In quantum theory, the lowest possible energy of a system is defined mathematically. A quantum oscillator cannot have zero energy. It possesses a ground state energy determined by its frequency. This quantity has measurable consequences. Yet it remains a number derived from the structure of the theory. The theory does not provide an ontology for it. Throughout physics, energy is measurable. It is calculable. It is conserved. It transforms according to precise rules. But it is never described as a physical substance, field, particle, or structure independent of the systems it quantifies. Energy is not listed among the constituents of matter. It is not localized like particles. It is not extended like fields. It is not geometric like spacetime. It is assigned. It is computed. It is conserved. When we say a system has energy, we mean that certain mathematical relationships hold. We mean that it can produce motion, heat, radiation, or work under specific conditions. We do not mean that a tangible entity called energy has been identified within it. Physics defines how energy changes. It does not define what changes. It defines how energy is transferred. It does not specify what is transferred. It defines conservation with extraordinary precision. It does not identify the conserved substance. This absence does not prevent physics from working. The predictions remain accurate. The equations remain reliable. Technologies based on energy calculations function with extraordinary success, but the omission remains. Energy appears in every major framework of physics. Classical mechanics relies on it. Thermodynamics formalizes it. Electromagnetism distributes it through fields. Relativity couples it to gravity. Quantum mechanics encodes it in operators. Quantum field theory permits its conversion into mass and radiation. Each theory depends on energy. None defines its ontology. Energy is everywhere in the equations and nowhere in the inventory of physical entities. It is indispensable. It is conserved. It is measurable. But it is not described as something that physically exists in its own right. Physics can calculate how energy transforms with extraordinary precision, but it cannot say what energy physically is.